Let's now look in depth at igneous rocks. Igneous rocks have diagnostic properties of colour and texture. Number 1, colour. The colour of an igneous rock can provide clues about its composition and the conditions under which it was formed. For example, rocks that are rich in iron and magnesium tend to be dark coloured, while those that are rich in silica tend to be light coloured. Rocks that are shades of green or pink often contain minerals like olivine or feldspar. The colour of an igneous rock can also be affected by weathering or alteration, which can cause it to become discoloured over time. Number 2, texture. The texture of an igneous rock refers to the size and arrangement of its crystals. Different textures can be used to identify the conditions under which the rock formed. For example, crystal size. The size of the crystals in an igneous rock can vary depending on the rate at which it cooled. Rocks that cooled slowly underground tend to have larger crystals than those that cooled quickly at the surface. These coarse-grained rocks with crystals over 3 millimeters are easily visible to the naked eye. Rocks that cooled quickly, on the other hand, tend to have smaller crystals, less than a millimeter, that are difficult to see even with a hand lens. Equicrystalline. If all the crystals in an igneous rock are about the same size, the rock is said to be equicrystalline. This texture can be seen in rocks that cooled at an even rate, such as basalt and peridotite. Porphyritic. Sometimes igneous rocks have two distinct crystal sizes. The larger crystals are called phenocrysts, while the smaller ones are called ground mass. Rocks with this texture are called porphyritic. Porphyritic textures can form when magma deep in the crust cools slowly, but is then intruded nearer to the surface to form the finer ground mass, resulting in 2 stages of cooling. Orientation. The orientation of the crystals in an igneous rock can provide clues about how it was formed. Usually, the crystals are randomly orientated, indicating they formed by crystallizing out from a liquid melt. Igneous rocks can be classified by both their texture and mineralogy. Texture refers to the size, shape, and arrangement of the crystals that make up the rock. Mineralogy refers to the types of minerals present in the rock. Let's look at peridotite. The texture is coarse with visible crystals, and its mineralogy is predominantly composed of olivine and augite. Basalt. The texture is fine with small crystals that are often not visible to the naked eye. Its mineralogy is composed of feldspar and augite. Andesite. The texture is medium with visible crystals, and the mineralogy is composed of feldspar, mica, quartz, and augite. Granite. The texture is coarse with large, clearly visible crystals, and its mineralogy is composed of quartz, feldspar, and mica. Overall, the texture of an igneous rock can give us an idea of the cooling rate of the magma or lava from which it formed. Rapid cooling, as in the case of basalt, results in small crystals, while slow cooling, as in the case of granite, results in larger crystals. The mineralogy of an igneous rock can tell us about the composition of the magma or lava from which it formed, as different minerals crystallize at different temperatures and pressures. So, the size of crystals in an igneous rock is related to the cooling rate of the magma from which it formed. The cooling rate affects the rate at which the minerals in the magma crystallize and grow into solid crystals, which then become part of the igneous rock. So to summarize, if magma cools quickly, there is less time for crystals to grow, and so the resulting igneous rock will have smaller crystals. This is because the minerals do not have time to grow large before the magma solidifies. An example of a rock formed from rapidly cooling magma is basalt, which typically has a very fine crystalline or even a glassy texture when erupted as lava at the surface. And on the other hand, if magma cools slowly within the Earth, there is more time for crystals to grow, and so the resulting igneous rock will have larger crystals. This is because the minerals have more time to grow and form larger crystals before the magma solidifies. An example of a rock formed from slowly cooling magma is granite, which typically has a coarse crystalline texture. Therefore, the faster the cooling rate, the smaller the crystal size, and the slower the cooling rate, the larger the crystal size. Magma viscosity is a measure of how easily magma flows when it is erupted onto the surface as lava. It is determined by the composition of the magma, its temperature, and the gas content. Magma viscosity affects the type of volcanic activity and the shape of volcanoes. Relatively passive volcanic activity, such as fissure eruptions, is associated with low viscosity magma. This type of magma is usually basaltic in composition and has a low gas content. Low viscosity magma produces lava at the surface that flows easily, allowing gases to escape, resulting in relatively gentle eruptions. Fissure eruptions occur when lava flows out of long, narrow cracks in the Earth's crust. The lava spreads out in a thin layer and cools to form a broad, flat, plateau-like landform. Examples of fissure eruptions include the Giant's Causeway of the Antrim coast in Northern Ireland, and the picture is below of this. Violent volcanic activity, such as central vent eruptions, is associated with high viscosity magma. This type of magma is usually andesitic or rhyolitic in composition and has a high gas content. High viscosity magma produces lava which is thick and does not flow easily, which causes gas bubbles to become trapped. This can result in explosive eruptions as the pressure of the trapped gases builds up and eventually bursts through the surface. Central vent eruptions occur when lava is ejected from a single central vent in the Earth's crust. The lava is often highly viscous, resulting in explosive eruptions that can send ash and rock fragments high into the atmosphere. Examples of central vent eruptions include the 1980 eruption of Mount St. Helens in the United States. The shape of a volcano is also influenced by magma viscosity. Low viscosity magma typically forms shield volcanoes, which have gentle slopes and broad flat tops. High viscosity magma, on the other hand, typically forms stratovolcanoes, which have steep slopes and a cone-shaped profile. This is because the highly viscous lava does not flow easily and tends to pile up around the vent, forming a steep-sided, cone-shaped structure. Shield volcanoes and composite cones, also known as stratovolcanoes, have different characteristics that can help you distinguish between them based on their size, shape, and composition. Shield volcanoes are generally much larger than composite cones and have a relatively gentle slope. They are formed by the eruption of basaltic lava, which is relatively fluid and tends to flow for long distances before solidifying. This results in a broad shield-like shape that is relatively flat at the top. The lava that forms shield volcanoes is typically low in viscosity, meaning it is relatively easy for the lava to flow out of the volcano. In contrast, composite cones are typically smaller and have a steeper slope. They are formed by the eruption of andesitic or rhyolitic lava, which is more viscous than basaltic lava, and therefore tends to build up around the vent of the volcano, rather than flowing far from it. The result is a tall, cone-shaped volcano with a steep, pointed peak. The layers of ash and lava that form composite cones are typically much thicker than those of shield volcanoes, and the eruptions can be more explosive. Now let's compare Kilauea and Mauna Loa and Mount Pinatubo and Mount St. Helens. Kilauea and Mauna Loa are both shield volcanoes located in Hawaii. They are both characterized by their large size and gentle slopes. Kilauea is the most active of the two, with frequent eruptions that are relatively non-explosive. Mauna Loa, on the other hand, has a longer history of explosive eruptions, although these are relatively rare. Mount Pinatubo and Mount St. Helens, on the other hand, are both composite cones located in the Philippines and the United States, respectively. They are both smaller than Kilauea and Mauna Loa and have steep slopes. Mount Pinatubo erupted in 1991 in a highly explosive eruption that caused significant damage to the surrounding area, while Mount St. Helens erupted in 1980 in a similarly explosive event that was one of the deadliest and most destructive volcanic eruptions in US history. In terms of composition, Kilauea and Mauna Loa are both formed by basaltic lava, while Mount Pinatubo and Mount St. Helens are both formed by andesitic lava. This difference in composition is reflected in the shape and size of the volcanoes, as well as the nature of their eruptions. Igneous bodies can be distinguished by their structure, form, and field relationships. Let's look at structure. Columnar jointing. This refers to the formation of hexagonal columns in igneous rocks due to the contraction of the magma as it cools and solidifies. These columns are often seen in volcanic rocks, such as basalt, and are formed perpendicular to the cooling surface. Pillow lava. This is a type of lava that forms when hot lava erupts underwater or flows into the ocean, causing the outer layer to cool quickly and form a crust. As more pillow lava flows into the crust, it balloons out like a pillow, creating a characteristic pillow-like structure. Now let's look at form. Lava flows. These are sheets of molten rock that flow out of a volcano and solidify on the surface. They can be distinguished from other igneous bodies by their thin, flat shape and the fact that they are formed on the surface. They are distinguished by baked margins at their base and often weathered upper surfaces. Sills. These are horizontal sheets of igneous rock that are formed when magma is injected between layers of pre-existing rock and solidifies. They are distinguished from other igneous bodies by their flat shape and their relationship to the surrounding rock layers. Sills show baking of the country rock both above and below. Dikes. These are a sheet-like body of igneous rock that cuts through and across layers of sedimentary rock at an angle to the bedding planes, discordant. They are distinguished by baked margins on both sides of the dike. Plutons. These are large, irregular-shaped bodies of igneous rock that form deep within the Earth's crust and are exposed at the surface through erosion. They can take a variety of shapes, but typically form large dome-shaped bodies that often bake the surrounding rock to form a metamorphic aureole. Now, finally, let's look at field relationships. Igneous bodies can also be distinguished by their relationships to other rocks and geological features in the surrounding area. For example, a sill that cuts across layers of sedimentary rock is likely to be younger than the surrounding rock layers, while a pluton that is exposed at the surface is likely to have cut through the surrounding rock layers. Baked and chilled margins. Baked and chilled margins are features that are formed when a hot intrusion, such as a magma body, comes into contact with cooler country rocks. The difference between the two depends on the degree of thermal alteration that the country rocks undergo. Baked margin is a zone of contact metamorphism that forms in the country rocks surrounding an intrusion. The heat from the intrusion causes the rocks to undergo recrystallization, resulting in changes to the mineralogy and texture of the rocks. Baked margins are characterized by the presence of new minerals, which form because of the higher temperatures. A chilled margin, on the other hand, forms at the edge of the igneous body when the magma cools rapidly against the colder country rocks. Chilled margins are characterized by a fine-grained or even glassy texture that results from rapid cooling. Metamorphic aureoles. Metamorphic aureoles are zones of contact metamorphism that form in the country rocks surrounding an intrusive body. The degree of metamorphism depends on the temperature and pressure conditions created by the intrusion. The width of the metamorphic aureole depends on the size of the intrusive body and the thermal gradient in the surrounding country rocks. The rocks in the metamorphic aureole are altered by the heat and pressure from the intrusion, resulting in changes to the mineralogy and texture of the rocks. The rocks closest to the intrusion undergo the most intense metamorphism, while the rocks further away are less affected. The rocks in the metamorphic aureole can be characterized by the presence of new minerals that formed as a result of the high temperatures. Discordant and concordant relationship. Discordant and concordant relationships refer to the relationship between an igneous body and the surrounding country rocks. A discordant relationship occurs when an intrusive body cuts across the layering or bedding planes of the country rocks. This is usually the result of magma forcing its way into existing cracks and fractures in the rocks. The resulting intrusion is characterized by sharp contacts between the intrusion and the country rocks. A concordant relationship, on the other hand, occurs when the igneous body runs parallel to the layering or bedding planes of the country rocks. This is usually the result of magma following existing weak zones in the rocks, as in a sill, or forming on the surface, as in a lava flow.